food, right? Food is being so oxidation of food, and we are producing small molecules like CO2, ammonia, water, right? So this is high energy. Food is high energy. Food has high energy, and in the process, we're giving electrons, right? So these electrons are captured by our oxidized coenzymes. So NAD plus, FAD, NADP plus, and also ADP plus PI. This is not actually taking electrons, but in the process of catabolism, um, it is part of the catabolic process. And in the process, what you're making is you're making NADH, okay, and we are making FADH2, NADPH, and ATP. Okay, then the reverse of that is going to be anabolism. So in anabolism, what we have is we're going uphill. These are precursors. So like amino acids, okay, glucose, for example, and etc., etc. So these guys are going to be made into complex molecules like cell wall, for example, glycogen, um, fat, okay, protein, things like that. And also we work. So these um, ingredients that are formed here, so these are sort of the chemical energy, okay? These are the chemical energy. Which helps us do the job. And in this process, these electrons and ATP, they're recycled. Okay, these guys are recycled back to the oxidized components for the cofactors. So this is anabolism, and this is our catabolism. So the cofactors are being reduced in the catabolic process, and they are being reoxidized in the anabolic process. Okay, just keep that in mind. So if you think about NAD plus and NADH, which one is going to be oxidizing agent, which one is going to be reducing agent? So let's say NAD plus, NADH, and we're trying to find out oxidizing and reducing. And in the process, we want to also find out which one is being oxidized and the other one is being reduced. All right, so which one is oxidizing between these two?
NAD plus.
Okay, NAD plus, because it oxidizes something, right? And reducing is going to be NADH. Okay, so oxidizing meaning it oxidizes something and itself get reduced, right? Yes or no?
Yes.
So being reduced is NAD plus and being oxidized is NADH. So which of these is actually accepting electrons?
NAD plus.
NAD plus is accepting electrons and NADH is giving electrons, right? Whichever gives electrons that is the reducing agent because it is reducing something else. Okay, and whichever accepts electrons, that is the oxidizing agent because it is accepting electrons from something else. So it is oxidizing that other compound and itself taking the electrons. All right. Okay, so yeah, that is the general. We already know. We talked about this last semester in the first class, anabolism, catabolism. This is an overview. Okay, so now what we also saw that all types of food that we ate, all of them were going into some central metabolites, right? Either pyruvate or acetyl CoA, right? So some central metabolites we have looked at. We have looked at pyruvate and acetyl CoA. Okay, so these are the two central metabolites. And so during catabolism, everything is sort of converging into these two primary central metabolites, right? All food, whatever we eat, everything is going to this simple, not simple, this common intermediates. So that is why catabolism is okay, is the converging part of the metabolism. So everything is converging into some common intermediates, all right? And then once we have these common intermediates, then those are acting as precursors. We're going to see all the details as we go along, as precursors to make complex molecules, right? So from these, common intermediates, we're making a bunch of other very, very complex molecules in the anabolic process, right? So anabolism is divergent. I should say convergent. And it makes sense the way nature does this because nature is very clever, right? So, if you think about it, it makes sense to break down all the complex food into some common intermediates and then process it all together to get ATP, right? Or produce the reduced coenzymes, right? So that everything goes through a common intermediate and we don't have to, the body doesn't have to evolve to handle each of the components totally separately. I mean, there are some separate processes at the beginning, yes, but somewhere in the middle, they are being converged so that you can use the same enzyme, right? You can use the same enzyme, same sets of enzymes to process all of that to get ATP. It makes total sense, right? And similarly, when you think about anabolism, okay, if you have simple precursors which are common, and then you can find a way to make these complex molecules, right? It makes sense that like when you are doing organic synthesis, you have some building blocks, and from that you can keep adding complex moieties onto it to make different types of molecules. So that's the same concept here in the anabolic process, where you're taking common intermediates and building complex forms of different cellular components. Right? It makes total sense. And that process, anabolic process, is I also should write that this is endergonic. So we need energy to make this happen. But it has to happen. So it must be overall delta G should be negative. But by itself, it is not going to be negative. So it needs help with something else. Okay, and that something else is more often than not is ATP. So ATP hydrolysis is what helps to make unfavorable reactions favorable. Okay, and that concept is called energy coupling. Yeah. So ATP hydrolysis, provides that energy needed to make anabolic processes occur in an overall exergonic manner. Okay, because individually the anabolic process is going to be endergonic, but that's not going to happen. So you need energy to give, and that is coming from ATP, from ATP hydrolysis. Okay, we're going to see examples of energy coupling concept. All right, so makes sense? And here catabolism is going to be exergonic. One thing also to note is that ATP synthesis by itself is an endergonic process. Okay, whenever we talk about synthesis or make something, it has to be always endergonic on its own. And when you talk about breakdown, more often than not, it is going to be exergonic. Okay, so I just want to write here that synthesis, let's write here. So synthesis equals endergonic. Inherently, these are endergonic. And if you break down something, that's going to be in general exergonic. There are many different types of reactions we're going to see organic reaction in this semester. We're going to see also some general types of reaction classifications and the importance of that in as it relates to the metabolic processes. So let's keep going. Yeah, this, hold on, let me just fix this. Okay, so since we're talking about ATP hydrolysis, let's we're going to talk about hydrolysis, but before that, just a couple of quick notes. Is that we know that if you have, for a general reaction, A moles of A and B moles of B going to C moles of C and D moles of D, then we can write this as equilibrium constant, right? So how do we write the equilibrium constant here?
Products over reactants.
So tell me how I should write it.
Are these concentrations? Then brackets, and then to the C.
All right.
And then
So
multiply by D. Yeah.
Yeah. So that's the component. Sorry, that's the number of moles going on as exponent. Okay. So remember, this is not additive, right? It is multiplicative. So you got to multiply the concentrations, not C plus D. Okay, keep that in mind. There's some confusion I see sometimes. So that's the equilibrium constant, and it is multiplicative, and the number of moles goes on the exponent. Okay. So then, what about delta G? Can we find delta G from this?
Is it RT ln of K?
So it's going to be negative RT ln of K, right? So for something to be spontaneous, delta G should be what? Plus or minus?
Negative.
Minus.
Negative. So this will be spontaneous. And if you have positive, then this is going to be, this is not spontaneous. What about the K equilibrium? What about this? What has to be the, what type of number we're looking for the K equilibrium to be if we want to make it spontaneous? So K equilibrium, we have two situations, one for the spontaneous, one for the non-spontaneous.
It should be greater than 1.
So it will be greater than 1, and here less than 1, because of the negative sign here. Okay, if you have within the natural logarithm, if the number is greater than 1, then you're going to get a positive number. And as a result, overall delta G is going to be a negative number because you have negative in the front. Okay, and conversely, if you have less than 1 within natural logarithm, then that is going to be negative. So the negative negative will be positive. Okay, we are just revisiting Gen Chem stuff, but there will be some math problems we're going to do, which will be important. So we using these equations. Okay. The other thing is that from here you can then calculate. How do you write then? The other way to write it is be ln k. I'm omitting the equilibrium. So ln k is going to be negative delta G over RT, right? So we can also find out k from here. It's going to be exponential negative delta G over RT, right? Yeah.
Yeah.
Okay. Um, all right. So now going back to the hydrolysis reactions. So typically, hydrolysis reactions are going to be hexagonic. Not typically, are always hexagonic. Always hexagonic. Okay. So if you take ATP, there are some numbers here where we have ATP. How many ways you can hydrolyze ATP, you think?
Three ways.
All right, so the first one, let's see ADP. Okay, let's do this as first. So ADP plus PI. And what's the other way?
AMP. AMP plus
Okay.
2PI.
AMP plus, so it is not 2PI, it is going to be PPI. Remember PPI from past semester?
It's like the pyrophosphate.
That's the pyrophosphate. Okay. And the PPI can also be hydrolyzed again. And now we're going to get 2PI. So there are some numbers here. The delta G for this first case is going to be negative 31 kilojoule per mole. If you make AMP, then it's going to be negative 46 kilojoule per mole. And the PPI is going to be around negative 19 kilojoule per mole. Okay, so that's our ATP. You should be able to write the structure of ATP. and so one more, and then this is the sugar. This is the sugar, and you have the base, nucleobase here, and we have OH here. And if it is a DNA, then there's no OH here, right? So that's the ATP. And so what we basically did is that in the first process, we made ADP. So the attack was here, and we got this opening, right? And when you make the AMP, then so this is the AMP. So to make AMP, we had to attack here, right? And we're talking about water. So water is the one that is attacking. Simple SN2 reactions, okay? That's how we make the AMP and ADP. And then when you have the PPI, so that's our pyrophosphate. So pyrophosphate is this. Go back to first semester notes. Okay, this also you can attack with water, right? Release that, so you get 2PI. Got it? Yeah.
Yep.
Yes.
All right. So yeah, depending on the metabolic process, if you have ATP and PI or AMP and PI, either way, or PPI, sorry, AMP and PPI, you're going to get overall hexagonic process, and that is going to help the anabolic process, which is endergonic. Okay, so that actually brings to this concept of energy coupling, and this energy coupling, we're going to see the main thing here is that the delta G is additive property. Okay, but K, equilibrium is actually multiplicative. So that's the main difference here. And what I mean by delta G additive is that if you have, let's say, a reaction A plus B going to C plus D, and then again C plus D going to E plus F. Okay, so if this has a delta G of delta G1, let's say this is endergonic, so it's plus 10 kilojoule per mole. And here in this process, this is delta G2. So this is negative 20 kilojoule per mole. So the net reaction is going to be, if you do net, now this is one thing you got to learn is how to do addition for equations, okay? So my left side and my right side, I have two sides, and trying to see if I can separate them. So this is my left side, right? And this is my right side. And so if I want to simply add them, okay, if you want to simply add them, add the left side stuff first, and then add the right side stuff separately. Do not mix left and right. Okay, so if you want to add them, simple addition, what I'll do is I'll write A plus B, okay, plus C plus D. Then this is going to, on my right side, so that's the left side. And right side I have C plus D plus E plus F. Okay, so that's the right side, and that's the left side. Now I wrote, if I add the equations, I must also add the numbers, right? So if I add the numbers, the delta G I'm going to get is going to be plus 10, okay, plus minus 20, right? Yes or no? Yeah, all I did is just add it. Make sense?
Yes.
So now this C plus D is on both sides, so it's going to cancel. And so we're going to get A plus B going to E plus F. And this process, the net delta G, so it's going to be delta G, okay, is going to be minus 10 kilojoule per mole. So basic thing I want to get across is how to do the math here, meaning that how to rearrange equations, how to do additions of equations. So do the left side first, right side second, do not mix them. And then simply add the delta G numbers, okay? So the thing to keep in mind here is that this first reaction by itself is endergonic. The second reaction itself is hexagonic, okay? But when you couple these two, then overall the reaction becomes hexagonic. Right? So that's the energy coupling concept. This is how we couple energy coupling. Okay? To make endergonic processes hexagonic by energy coupling. Yeah, everybody with me?
Yes, sir.
Now, one thing to keep in mind that if you flip the sign, okay, if you flip the sign, then so for example, what is given here, A plus B going to C plus D is delta G1, which is plus 10. Now, if you write that as C plus D going to A plus B, so basically we flipped it, okay, then the delta G going to be, we're going to flip the sign also. Right, we're going to do examples of how that works out. Right, and then if you flip the one on the bottom, if is going to be E plus F going to C plus D, then the delta G2 is going to be, then we're going to flip that, so plus 20 kilojoule per mole. So now if you do the net, okay, you're going to get, so CD will cancel again. So E plus F going to A plus B. Now your delta G is going to be minus 10 plus 20. So it's going to be plus 10 kilojoule per mole. So essentially the net reaction here, okay, flip the sign. Meaning that you can make E and F from A and B, which will be hexagonic, but if you try to make A and B from E and F, then it will be endergonic. Make sense? So if you flip the equation, then you got to flip the sign as well. Got it?
Got it.
All right. So ATP hydrolysis is hexagonic. Why is that? Is there a chemical reason you can think of why it will be the case?
The products are more stable.
And why is that?
The phosphodiester bond is inherently unstable.
to do with like the localization and delocalization of electrons?
So it has to do with charges, right? So we have better. So there's a lot of charge, negative charge, in the ATP. When you hydrolyze it, then you dissipate some of that charge, right? So basically, you have better charge separation. In the product. That's one reason. The other reason is that because these are all polar, if you break it down, you're going to solve it, the product, more than the reactant. So better solvation is another reason. Solvation with water. Okay. Okay. And so overall, that's why these are. So it's going to stabilize. The product. Okay, let's take a break, quick break, 1 minute, and then we'll come back. Okay.
Someone asked, what do you mean by better charge separation in the product?
Better charge separation.
Yes, sir, like in the product.
So there's less charge in the product than in the reactant. So there's a lot more charge in the reactant and less charge in the product. Okay. So if you look at ATP, we got 1, 2, 3, 4 negative charges, right? And if you look at AMP, we'll have only 1 charge. So not everything is concentrated in one molecule. Okay, you're splitting the overall charge between 2 molecules. So that's why you're separating the charges better in the product than what it is in the reactant. Make sense? Yeah. Okay, all right, let's get back. So ATP is a high energy compound because when it hydrolyzes, it gives a lot of energy. But there are other molecules that we're going to come across which are even higher energy compound than ATP. Right? So if you hydrolyze those compounds, you get even more ATP, more energy than ATP. So one of them is going to be, we'll see this so many times during the semester, is going to be phosphoenol pyruvate. Is going to be also called PEP. That's a short form. So just to know that PEP is the phosphoenol pyruvate. Okay. Anyone knows the structure of pyruvate?
It's 2 carbons. There's a carbonyl.
Mm-hmm. It has a carbonyl, yeah.
It's an alpha keto acid.
Right, that's the pyruvate. So if you, I mean, the way I remember this is that I know acetate, right? That's acetate. So all I have to do is I got to add a carbonyl in between, right? That's all it is. Going from acetate to pyruvate. So pyruvate we're going to abbreviate as, so we're going to abbreviate as PYR throughout the semester. So that's going to be pyruvate. And this is a keto form, right? It can tautomerize into this enol form, right? Keto-enol tautomerization, organic chemistry, you remember? Yeah or no?
Yes.
So that's the keto, so this is the keto form, right? And that's the enol form. So this is the enol. So phosphoenol, that's my enol, right? And to add the phospho, how do I do it? I got to add just that phosphorylate, that CH, that OH group. So all I got to do is double bond CO, okay? And here I'm going to phosphorylate, add a PI, okay? So we're also going to abbreviate this guy right here throughout the semester as PO3 2 minus. So the way we're going to remember this as going to be CH2 double bond CO, PO3 2 minus, and CO2 minus. So that's the phosphoenol pyruvate. Okay, this is PEP. So this is even a higher energy compound, even higher than ATP. So if you hydrolyze it, okay, you're going to have water, and PI is going to leave. We get this OH and CO2 minus. So that's the enol form. And then this will tautomerize, okay, tautomerize to go to the keto form. Okay. And here the delta G is actually negative 62 kilojoule per mole, so much higher. So if a compound is high energy phosphate compound, it can do phosphoryl transfers to a lower energy compound. So what I mean by that, so we just saw that the ATP, okay, hydrolysis is going to be negative 31, and here is going to be negative 62. So what that means is that if you take PEP, phosphoenol pyruvate, and ADP, okay, so let's just do this. It's one thing I need to talk about, but I'll catch up on that. So we have PEP, and it's phospho, so I got to add the color. Let's just do a color on the PEP here, plus ADP, and we're going to get pyruvate plus ATP. So P is, right, phosphoenol pyruvate, and that phospho is going to the ADP to make PI. So essentially you are making ATP from PEP because PEP is a higher energy phosphate compound than ATP. Okay, so this is one of the states in glycolysis we're going to see that if you remember the chart we did last class, we make 2 ATP directly from glycolysis. And so this is one of that steps. Okay. All right, so that's another high energy compound, and that is going to be your 1,3-BPG. So We spent so much time on BPG last semester in the hemoglobin chapter, right? BPG is a negative allosteric regulator, but this is not the same BPG. So there we had 1,2 BPG, but here we have 1,3 BPG. Okay, so we got 1,3 BPG. So this is another high energy compound. We got PEP. So let's see. Let me, if I want to rank them. So PEP is going to be really high. Then we got 1,3. You don't have to remember any relative energy or anything like that. Just know the general idea of this phosphoryl transfer reaction. So then we got phosphocreatine. We're going to see that later. So just, you don't even have to remember that name right now. TINE, phosphocreatine is another high energy compound. ATP is also high energy compound, but it's much lower. So ATP is going to be over here. And then these guys, okay, so if you then draw a line, these are all our, let's say this is our toolbox, okay, of high energy compound. And they are going to do phosphoryl transfer reactions. For example, all of these guys can make ATP, okay. And then in general, from ATP, you're going to see a lot of phosphoryl transfer reactions to sugars, for example, glucose, okay. So glucose, if you have glucose, then we get, this is, G6P, glucose 6-phosphate. So glucose is going to accept that PI from ATP, okay. Also glycerol can accept that PI to make glycerol phosphate, but generally glucose 6-phosphate is what we're going to we'll look at a lot, okay, throughout the semester. So just to recap, what I'm trying to get across here is that the high energy compounds can transfer phosphoryls to lower energy compounds. That is the main bottom line here. And even more high energy compound are there than ATP. So PEP, 1,3-BPG and phosphocreatine. So those compounds can make ATP, okay? So we can make ATP from those compounds and they can do phosphoryl transfer reactions. And then once we have ATP, then because it is present in very high concentration, much higher than equilibrium concentration in our cells, general metabolic processes will look for ATP as a pool when we need to phosphorylate those compounds, okay? So glucose, the first thing happens from the blood glucose when it is uptaken into cells is that it will undergo phosphorylation. That's the first thing that happens all the time. And that phosphorylation process, you make glucose 6-phosphate, G6P. Okay, more often than not, you make G6P. Sometimes you make G1P, but G6P is the main. That's the first thing happens whenever glucose is uptaken into cells from blood, and ATP is what makes that happen. So if you look at the ATP one more time, just see what type of reactions could happen. And again, we're building the vocabulary so that when you do specific examples, then it will be much easier to come back to this and recall, okay? So I'm just going to make that as A, so adenine, right? So this is our ATP. And then generally, if you think about glucose, right? So glucose, we did so many structures of glucose last semester, the alpha beta form, the pyranose form, so much we did, the disaccharides, whatever not. But generally glucose, you'll have that one of the oxygens which can act as a nucleophile. So if you're making G6P, it is going to be the oxygen on the 6th carbon, right? Recall glucose structure. The number 6 carbon is going to be the oxygen attached to that number 6 carbon is going to be the nucleophile. So if I just RO, if I just want to write that as RO or RO minus, whatever you want to call it as, okay, and this is going to be then acting as a nucleophile. Here, if you attack there, then you release, then you can also attack here and release, and yet again you can attack here, okay, and release this. So 1, 2, and 3. So in 1, what we're going to get? In 1, we're going to get just ROPI, right? Plus ADP. And in 2, we're going to get RO PPI plus AMP. And if we do third, we're going to get RO is going to be A, right? That's the ADP plus PPI. So general nomenclature, this is the phosphoryl transfer reaction, phosphoryl, because all we are doing is we're transferring a phosphoryl, which is the PI. So most of the time, this is what we're going to see, like glucose to glucose 6-phosphate is a phosphoryl transfer reaction. And this is going to be our pyrophosphoryl transfer reaction, because we are transferring pyrophosphate. And then finally here, this is going to be so this will be adenylyl transfer reaction, because we are transferring the adenine group, okay? So yeah, we are going to come back to each of these as we go along the semester and specific examples. So this last example, we're going to see when we make glycogen, for example. So when we synthesize glycogen, this is one of the steps that happen. Okay, yeah, we'll talk about the details later, but just keep that in mind that ATP is a very important ingredient. Not only it can make endergonic processes hexagonic by energy coupling, but it can also act as a source of phosphoryls or the adenine group to be attached to glucose, for example, to participate in many metabolic processes. So these are the two main concepts that I am trying to get across here. Make sense?
Yes.
Are we good here? Yeah.
Yes, sir.
Okay. So we have been looking at ATP quite a lot, and as we are doing hydrolysis, another compound we'll see a lot is going to be acetyl-CoA. And this is anyone remembers what is the general classification of this compound from the last semester? Like what I'm looking for are going to be alcohol, aldehyde, ester, thioester, acid, any of these classifications. So this is acetyl-CoA is a thioester. And someone tell me how to write the general structure of a thioester.
Is it a carbon with a double bonded O and then a sulfur?
Okay. So that's my thioester. And so that is, general structure of acetyl-CoA. It is a thioester compound. And the main difference between, so if we consider thioester versus our regular ester, let's just keep it here. There's a reason why I keep it there. So if you take a thioester and a general ester, right, which one do you think will have higher energy between these two compounds?
Thioester.
Thioester, right? Because so here you'll have a better resonance stabilization, right? In the ester. So yeah, I can write of delta plus, delta minus, whatever. And so ester is going to be more resonance stabilized because of the oxygen that is present. It can participate in resonance stabilization. And we have seen that a lot of examples in like organic chemistry. But that type of stability is not here in the thioester because it's sulfur, right? It's the next on the group on the row. So inherently, the thioester will be a higher energy compound than the ester. So if you hydrolyze thioester and ester, we're going to get, so let's say water and water, both cases. So it is going to be attacking there, and you're going to release that RSH. Same thing here. This will be, yeah, attacking that bond. You're going to release that. So in both cases, you're going to get that. Okay. Here we'll get RSH, and here we're going to get ROH. So the final delta G is same for both, but just because the delta G for the thioester, not the delta G, the relative stability, free energy was higher, right? In the thioester case, the net delta G we're going to get from hydrolysis of the thioester is going to be much higher than ester. Okay, so delta G, let's say 2, and this will be delta G1. It's just because they are, you're starting at a higher energy. So when you hydrolyze, you get more out of it than what you have for ester. Generally, the specifics are not that important, but just know that thioester is a high energy compound, and acetyl-CoA we're going to see a lot of it. So just that's why I brought this up. And acetyl-CoA hydrolysis, the delta G for a thioester generally is going to be again quite high, about negative 31 kilojoule per mole. So this is another high energy compound, thioester. Okay. All right, I think we'll probably have time to touch one more thing. So far we have been looking mostly about hydrolysis reaction and group transfer reactions like phosphoryl transfer reactions. But if you think about the general thing in catabolism, what happened is that the food got oxidized, right? And to carbon dioxide and water. So if you think about oxidation, so that is an oxidation process, oxidation of food. So if we have glucose, what is the chemical formula of glucose?
C6H12O6.
And we have oxygen, right? And what do you think will be the product after catabolism if you catabolize glucose all the way? You can only make two things,
Just carbon dioxide and water.
just carbon dioxide and water, right? So we need 6 carbon here, so I'm going to get 6 CO2. And I have 12 hydrogen, so I got to balance it by 6. And so 6 plus 12, 18, I have 6, I need 6 more here. So this is like burning when you burn, right? Burning food, that's what is happening. Burning glucose to make CO2 and water. This has a very high, really high delta G, and that's going to be negative 2840 kilojoule per mole, very high. If you take a fatty acid, for example, okay, we looked at a lot of fatty acid structures. So palmitate is a, we don't need, I don't know the general formula for that, but it is a 6 carbon. Well, we can figure that out, but we don't have to. So palmitate, not 6, C16, it is a 16 carbons here. Okay, so if you have palmitate, and you need 23 oxygen molecules to go to 16 CO2 and then 16 water. So because you have more carbon here, 16 over here than 6, okay, and much less oxygen than glucose. So palmitate is more reduced than glucose, so you can oxidize it even more than glucose. So that's why the delta G here is going to be really, really high. Okay. So that's why the overall energy you get from food. Okay, if you eat fat, you get a lot more energy, a lot more ATP than what you get from sugar. That's the bottom line I'm trying to get across. Okay, if you take 1 molecule of glucose versus 1 molecule of palmitate from a fat source like almonds or whatever, you know, then you're going to get a lot more ATP, okay, from it, because the delta G is going to be really high, highly negative. So you get a lot more energy than from glucose. But glucose is a quick source of energy, so that's there because it can be easily uptaken by cells from the blood and made into ATP. But fats are very good source of storage. So that's why bears can go through the winter without eating, because there's so much, they eat so much right before hibernation that all that is stored in their fat, in their body fat, and slowly that fat is, you know, oxidized to give them ATP. Right. So if you think about it again, the glucose is being oxidized. So in the process, something else is being reduced, right? What is being reduced? Our cofactors. Yeah. So we are making NADH, FADH2 from glucose oxidation. Same thing happening with the fat that we eat. We are making NADH, FADH2. But because there is so many carbons here in the palmitate, and it is much more reducing to start with than glucose, we will make a ton of NADH and FADH2 from palmitate than what we're going to make from glucose, right? Because we're oxidizing palmitate a lot more than what we're doing with glucose. So as a result, all those electrons, a lot more electrons are going to be given up by palmitate than glucose. So in the process, we will generate a lot more of NADH and FADH2 and NADPH than what we will in the glucose oxidation. Make sense? Do you see the general idea I'm trying to get across? So everything comes down to, again, you know, oxidation is catabolism, catabolism is oxidative, and anabolism is reductive. So we are oxidizing food, and all those electrons going to you know, the coenzymes which are accepting it, and those are going to be fed into the ETC to make ATP. Make sense?
Yes.
Yeah.
All right, so we're going to stop here. Our first quiz is going to start next Tuesday, and this is the first time I'm going to give a quiz on Blackboard. And I hope I don't mess it up. I'll try to do but there are chances that something could go wrong in the first time, okay? So don't worry about it. If it does happen, then we'll make it on the next Thursday if I find out there's something wrong. But I think it should be okay. But I'm saying just in case if something happens, then we should be able to retake that Thursday. But it will open up at 12:05, and if you look at, as we talked about, you'll have 10 minutes to complete, but you'll have about 20-minute window to take that quiz, so that it should be done in the class time. Also important is that it will be enabled in Proctorio in Blackboard, so make sure that you have that Google Chrome and all these things. Everybody has used Blackboard Proctorio, right, for your other tests. I can't imagine that you have not, because everything is online now. Okay, so please make sure you have your microphone and webcam working. Otherwise, you will not be able to start the quiz, and that's the Proctorio setting is that. And there will be five questions generally in the quizzes, and it will be based on the general concepts is what we have been talking about, the general concepts from the last two lectures. No math yet because we haven't done examples, so there will be no math. It will be based on general examples. So next class, we're going to look at some redox reactions, and we should be able to also do a worksheet to do all the math. Okay, so I'm hoping by next Thursday, we should be able to get started on glycolysis.
What time does the quiz close on Thursday? You said it opens at 12:05, but what time does it close?
12. So it will not Thursday. The quiz is on Tuesday.
Tuesday, sorry.
Yeah, it will close at 12:25. But you'll have 10 minutes to take the quiz.
Thank you.
Just like last semester.
Have a good evening.
All right. I will see you guys on Tuesday.
Have a great week and weekend.
You too.